Hello everyone, I'm Shair Mog. Last month I talked to you about modular monolith and the value of modern monolithic architecture. One of the more interesting discussions that came out of that post and video is the inverse discussion. When is it right to still pick microservices? Like any choice, the answer is subjective and depends on many things, but there are still general rule of thumbs and global metrics we can use. Before we get into these problems, we need to understand what it means to have a microservice architecture. Then we can gauge the benefit and price of having such an architecture. A common misconception is that microservices are simply broken down monoliths. This isn't the case. I've talked to quite a few people who still hold that notion. To be fair, they might have a point. This is how AWS defines microservices. This is a bit of a mouthful, so let's go over this one part at a time. The definition starts with the words architectural and organizational approach to software development. The most important thing about microservices is how they are organized. The fact that we can break down the system and work with smaller projects helps us organize our team better. This is the primary benefit of microservices. The rest of the sentence talks about composing software from small independent services that communicate over well-defined APIs. There are several interesting points in this sentence. First, the word composed. There's a lot of heavy lifting here. In a monolith, we don't really compose software, we write it. With microservices, a lot of the heavy lifting is composition. We connect separate services and wire them to one another. The well-defined API part hints to another concept. With microservices, we have as many products as there are microservices. Every one of these services is a standalone product with its own API. Small, self-contained teams go back to the point we made initially when discussing the fact that this is an organizational pattern, but they include two important details. Small teams are a crucial concept in large enterprise deployments. Self-contained is another major detail. A monolith split into smaller elements isn't self-contained. We will get back to this point. This part I don't like. It makes promises without defining constraints. Easier to scale, faster to develop, faster time to market. Such claims need to be qualified, and this definition doesn't qualify them. It isn't necessarily wrong, but we need a way to understand when these benefits can come into play and what are the trade-offs we make. Smaller monoliths might fit the definition, but they don't if you read between the lines. The words independent, easier to scale hint at the problem. The problem and advantage of a monolith is a single point of failure. By having one service, we can usually find problems more easily. The architecture is much simpler. If we break this service down into smaller pieces, we essentially create a distributed point of failure. If one piece along the chain fails, the entire architecture breaks down. That isn't independent and it isn't easier to scale. Microservices are not small monoliths, and breaking down the monolith isn't only about working with smaller projects. It's about shifting the way we work. A good microservice needs to follow these principles for robustness and scale. When we say divided by business function, we're referring to a logical division. A microservice is a standalone product that provides a complete package. This means that the team responsible for the microservice can make all the changes required for the business without dependencies. So, good examples for microservices would be billing, invoicing, user tracking, etc. Bad examples would be database service, web, or business logic. as one block. In red, we can see the more traditional layered architecture, which is very different conceptually from microservices. Automation through CI/CD is crucial for microservices. Without continuous delivery, the cost of updating would eliminate every benefit of microservices. Independent deployment is implied, since a commit on one microservice can only trigger the CD of that specific service. We can accomplish this through Kubernetes and infrastructure as code. A microservice should hide the underlying implementation details. A service acts as a standalone product that publishes an API for other products. We commonly accomplish this via REST interfaces, but also messaging middleware. This is further enhanced with API gateways. Decentralized with no single point of failure, otherwise we would distribute failure. Failure should be isolated. Without this, single service going down could create a domino effect. Circuit breakers are probably the most important tools for isolating failures. To satisfy this dependency, every microservice handles its own data. This means many databases, which can be challenging at times. Observability is required to deal with failure on scale. Without proper observability, we are effectively blind, as the various teams can deploy automatically. This is all good and well, but what does that mean in practical terms? Most of what it means is that we need to make several big changes to the way we handle some big ideas. We need to move more of the complexity to the DevOps team. We need to handle cross-microservice transactional state differently. This is one of the hardest concepts to grasp when dealing with microservices. In an ideal world, our operations will be simpler and contained in a small microservice. The service mesh framework surrounding our microservices will handle all the global complexities and manage our individual services for us. But that isn't the real world. In reality, our microservices might have transactional state that carries between the services. External services might fail, and for that, we need to take some unique approaches. If your company doesn't have good DevOps and platform engineering teams, microservices aren't an option. Instead of deploying one application, we might deploy hundreds because of a migration. While the individual deployments are simple and automated, you will still throw a lot of work at operations. When something doesn't work or doesn't connect, when a new service needs to integrate to the service configuration should be adapted. Operations carry a greater burden when working with microservices. This requires great communication and collaboration. It also means the team managing a specific service needs to take some of the ops burden back. That isn't a simple task. As developers, we need to know many of the tools used to tie our separate services back to a single unified service. Service Mesh lets us combine separate services and effectively acts as a load balancer between them. It also provides security, authorization, traffic control, and much more. API gateways should be used instead of invoking the API directly. This can be awkward at times, but it's often essential to avoid costs, prevent rate limiting, and more. Feature flags and security secrets are useful in a monolith as well, but they're impossible to manage at microservice scale without dedicated tools. Circuit breaking lets us kill a broken web service connection and recover gracefully. Without this, a single broken service can bring down the entire system. Identity management must be separate. You can't get away with an authentication table in the database when dealing with a microservice environment. I'll skip orchestration, CI/CD, etc. they too need to be adapted for every service that comes out. Some of those tools are opaque to developers, but we need the help of the DevOps team in all the phases. Stateless services would be ideal. Carrying a state makes everything more complex. If we stored the state in the client, we need to send it back and forth all the time. If it is on the server, we would need to either fetch it constantly, cache it, or save it locally, and then all interaction would be performed against the current system. That eliminates the scalability of the system. A typical microservice will store into its own database and work with local data. A remote data that needs information will typically cache some data and to avoid round trips to the remote service. This is one of the biggest reasons microservices can scale. In a monolith, the database should become the bottleneck of the application. That means the monolith is efficient and limited by the speed we can store and retrieve the data. This has two major drawbacks. The more data we have, the larger the database and performance impacts all users at once. Imagine querying an SQL table of every purchase ever made on Amazon just to find your specific purchase. Databases have different use cases. Some databases are optimized for consistency, write speed, read speed, time data, spatial data, and more. A microservice that tracks user information would probably use a time series database, which is optimized for time-related information, whereas a purchase service will focus on a traditional conservative ACID database. Note that a monolith can use more than one database. That can work perfectly well and can be very useful, but it's the exception, not the rule. The Saga pattern works by using compensating transactions to undo the effect of a Saga if it fails. When a Saga fails, the compensating transaction is executed to undo the change made by the previous transaction. This allows the system to recover from failure and maintain a consistent state. We can accomplish this with tools such as Apache Camel, but this is non-trivial and requires far more involvement than a typical transaction in a modern system. That means that for every major cross-service operation, you would need to do the equivalent undo operation that will restore the state back. That is non-trivial. There are several tools for Saga orchestration, but this is a big subject that is beyond the scope of this video. I'll just explain this in broad terms. Let's say we have money transfer process. For this to work, we need to first allocate funds. Then verify that the recipient is valid and exists. Then we need to deduct the funds from our account. And finally, we need to add the money to the recipient's account. That is a successful transaction with a regular database. This would be one transaction. If a failure occurs when allocating funds, we need to remove the allocation. So we need to create a separate block of code that does the inverse operation of the allocation. If verifying the recipient fails, we need to remove that recipient, but then we need to also remove the allocation. If deducting the funds fails, we need to restore the funds, remove the recipient, and remove the allocation. Finally, if adding the funds to the recipient fails, we need to run all the undo operations. What's important to understand about Saga is that it avoids the classic ACID database principles and focuses on eventual consistency. That means operations would bring the database to a consistent state at some point. That is a very difficult process. Imagine debugging a problem that only occurs when the system is in an inconsistent state. Another problem in Saga is illustrated in the CAP theorem. CAP stands for consistency, availability, and partition tolerance. The problem is we need to pick any two. Don't get me wrong, you might have all three, but in a case of a failure, you can only guarantee two. Availability means that requests receive responses, but there's no guarantee that they contain the most recent writes. Consistency means that every read receives the most recent writes on an error. Tolerance means that everything will keep working even if many messages get dropped along the way. This differs greatly from our historic approach to failure with transactions. Hopefully, you now understand how hard it is to deploy microservices properly. We need to make some big compromise. The new way isn't necessarily better. In some regards, it is worse. But the proponents of microservices still have a point. We can gain a lot by microservices and should focus on those benefits too. We mentioned the first requirement up front, DevOps. Having a good DevOps team is a prerequisite to considering microservices. I saw teams trying to hack their way through this without an ops team, and they ended up spending more time on operational complexity than writing code. It wasn't worth the effort. The biggest benefit of microservice is to the team. Splitting teams to vertical teams that work independently is a tremendous benefit. The most modular monolith in the world can't compete with that. When we have hundreds of developers following the Git commits alone and tracking the code changes in scale, it becomes untenable. The value of microservices is only realized in a large team. This sounds reasonable enough, but in a startup environment, things shift suddenly. A colleague of mine works for a startup that employed dozens of developers. They decided to follow a microservice architecture and built a lot of them. Then came the downsizing, and maintaining dozens of services in multiple languages became a problem. Splitting a monolith is hard, but doable. Unifying microservices to a monolith is probably harder. I'm unaware of anyone who seriously tried to do that, but would be curious to hear stories. In order to move to a microservice architecture, we need a bit of a mind shift. A good example is in the database. A good example would be user tracking microservice. In a monolith, we would write the data to the table and move on with our work. But this is problematic. As data scales, this user tracking table can end up containing a great deal of data that is hard to analyze in real time without impacting the rest of the operating system. With a microservice, we can offer several advantages. The interface to the microservice can use messaging. That means the cost to send tracking information will be minimal. Tracking data can use a time series database, which would be more efficient for this case. We can stream the data and process it asynchronously to derive additional value from that data. There are complexities. Data will no longer be localized. So if we send tracking data asynchronously, we need to send everything necessary, as the tracking service won't be able to go back to the original service to get additional metadata. But it has a locality advantage. If regulation changes about tracking storage, there's a single place where this is stored. Did you ever push a button to a release that broke production? I did. More than once. Way too many times. That's a terrible feeling. Microservices can still fail in production and can still fail catastrophically, but usually their failure is more localized. It is also easier to roll them out to a specific subset of the system, canary, and verify. These are all policies that can be controlled in depth by the people who actually have their fingers on the user's pulse. Ops. Observability for microservices is essential, expensive, but also more powerful. Since everything occurs at the network layer, it is all exposed to the observability tools. An SRE or a DevOps can understand a failure with greater details. This comes at the expense of the developer, who might need to face increased complexity and limited tooling. Applications can become too big to fail. With modularity, some of the largest monoliths around have so much code, it takes hours to run through a full CI/CD cycle. Then, if the deployment fails, reverting to the last good version might also take a while. Back in the day, we used to divide teams based on layers: client, server, DB, etc. This made sense since each of those required a unique set of skills. Today, vertical teams make more sense, but we still have specialists. Typically, a mobile developer wouldn't work on the back end, but let's say we have a mobile team that wants to work with GraphQL instead of REST. With a monolith, we would either tell them to live with it, or we would have to do the work. With microservices, we can create a simple service for them with very little code, a simple facade to the core services. We won't need to worry about a mobile team writing server code, since this would be relatively isolated. We can do the same for every client layer. This makes it easier to integrate a team vertically. It is hard to put the finger at the size that makes a monolith impractical, but here's what you should ask yourself. If you have a couple of teams, then a monolith is probably great. If you have a dozen teams, then you might face a problem here. As a project grows, your pull requests will spend more time waiting to merge, and issues will take longer to resolve. This is inevitable as complexity tends to grow in the project. Notice that the new project will have larger features, and that might sway the results. Once you account for that in the project stats, the decrease in productivity should be measurable. Notice that this is one metric. In many cases, it can indicate other things, such as the need to optimize the test pipeline, the review process, modularity, etc. At some point, a huge project becomes so big that the experts start losing track of the details. This becomes a problem when bugs become untenable and there's no authoritative figure that can make a decision without consultation. Microservices will cost more. There's no way around that. There are special cases where we can tune scale, but ultimately observability and management costs would remove any potential cost savings. Since personnel costs usually exceed the cost of cloud hosting, the total might still play in your favor, as those costs might decrease if the scale is big enough. The trade-offs of monoliths versus microservices are illustrated nicely in the following radar chart. Notice that this chart was designed with a large project in mind. The smaller the project, the better the picture is for the monolith. Notice that microservices deliver a benefit in larger projects in fault tolerance and team independence, but they pay a price in cost. They can reduce R&D spend, but they mostly shift it to the DevOps, so it isn't a major benefit. The complexity of microservices is immense and sometimes ignored by the implementing team. Developers use microservices as a cudgel to throw away parts of the system they don't want to maintain, instead of building a sustainable, scalable architecture worthy of replacing a monolith. I firmly believe that projects should start off with a monolith. Microservices are an optimization for scaling a team, and optimizing prematurely is the root of all evil. The question is, when is the right time to do such an optimization? There are some metrics we can use to make that decision easier. Ultimately, the change isn't just splitting a monolith. It means rethinking transactions and core concepts. By starting with a monolith, we have a blueprint we can use to align our new implementation as it strengthens uh, its design. Thanks for watching, and please check out my book and follow me for more videos like this. Thank you.